Hello there and welcome to our channel, where curiosity slows down, science softens its voice, and the long story of our planet is told at a pace meant for unwinding rather than rushing. This is a place for gentle thinking, for letting questions linger without demanding answers right away, and for taking a quiet walk through ideas that are usually presented far too quickly. Tonight, we're stepping back into a version of Earth so old and unfamiliar that even the continents themselves hadn't yet learned how to be apart. Before we wander too far into that ancient world, take a small moment to notice where you are right now. Maybe you're listening from a bedroom lit only by a phone screen, or perhaps from a sofa after a long day, or somewhere halfway between sleep and wakefulness. What part of the world are you in tonight? And what time is it where you are? It's a simple question, but fitting because this story takes place in a time when clocks didn't exist. Calendars were meaningless, and the planet itself kept time and movement so slow they would have felt invisible to anything alive back then. If you find this kind of quiet exploration calming, or if it helps your thoughts slow down as the day fades, you're always welcome to like the video or subscribe. It helps this small, peaceful corner of science reach others who might also be looking for something steady and unhurried to end their day. And now, with nothing pressing to do and nowhere in particular to be, let's ease ourselves into a very different Earth. Imagine waking up on a planet where nearly all the land you could ever walk across was connected. No oceans separating continents, no familiar outlines of Africa, Asia, or Americas. Instead, one vast stretch of land stitched together into a single supercontinent that geologists would one day call Pangea. From space, if anyone had been there to look, Earth would have appeared simpler, almost tidier, like a puzzle assembled into one massive piece surrounded by an enormous global ocean. Life on Earth during Pangea was shaped by that unity in ways that are difficult to picture today. When all the land was joined together, distance meant something different. Climate behaved differently. Seasons followed unfamiliar patterns. Creatures migrated not between continents, but across entire hemispheres without ever touching salt water. Rivers ran for thousands of kilometers without interruption. Deserts sprawled across interior, so far from the sea that rain clouds rarely reached them. This was not a gentle or balanced world. Pangea existed for hundreds of millions of years, forming gradually and then breaking apart just as slowly. During that long span, life had to adapt to extremes. Inland regions baked under relentless heat. Coastal areas experienced long stretches of wet and dry seasons that lasted for years rather than months. Temperature swings could be dramatic, especially far from the moderating influence of the ocean. At the heart of this supercontinent, the air itself felt different. Carbon dioxide levels were often higher than today, and oxygen levels fluctuated depending on the era. These changes influenced everything from plant growth to animal size. Forests could spread widely during wetter periods, only to retreat when conditions dried. Vast plains opened up where trees struggled to survive, and creatures living there had to be built for endurance rather than abundance. Plants were among the first to truly define what life on Pangea felt like long before flowering plants existed. The land was dominated by ferns, seed ferns, cycads, and towering conifers. These plants didn't rely on insects in the way modern flowers do. Many released clouds of pollen into the wind, trusting chance and air currents to carry their genetic material across great distances. In a world without fragmented continents, that strategy worked remarkably well. Forests during certain periods were dense and expansive, but they didn't resemble modern forests. The ground beneath them was often spongy, layered with decaying plant matter. In earlier times, especially during the late Paleozoic, massive swamp forests flourished near coastlines and river systems. These environments would eventually become the coal deposits that fueled human industry hundreds of millions of years later, though nothing living then could have known that. Insects thrived in these forests, some growing to sizes that feel almost unreal today. Dragonfly-like insects with wingspans wider than a human arm glided through humid air. Their size wasn't a coincidence. Higher oxygen levels allowed their simple respiratory systems to deliver enough oxygen to larger bodies. Beetles, millipedes, and early relatives of cockroaches filled ecological roles that had no modern equivalent. Moving across the land, reptiles began to take center stage. Amphibians had dominated earlier landscapes, tied closely to water for reproduction. But reptiles, with their waterproof skin and shelled eggs, were better suited to the dry interiors of Pangea. They could travel farther from rivers and lakes, colonizing environments that would have been inaccessible to their ancestors. These early reptiles were not yet dinosaurs, but they laid the groundwork for what would come later. Some were small and agile, feeding on insects or plants. Others grew larger, becoming apex predators of their time. Their success was tied directly to Pangea's geography. With no continental barriers, successful adaptations could spread widely, leading to relatively similar species appearing across vast distances. The oceans surrounding Pangea were just as important as the land itself. A single massive ocean, often called Panther Lassa, wrapped around the supercontinent. Coastal waters teemed with marine life, including early sharks, bony fish, and marine reptiles that would later dominate Mesozoic seas. Coral reefs existed, though they were built by organisms different from modern corals. Despite this abundance along the edges, the interior of Pangea could feel empty by comparison. Water was scarce in many regions. Rivers were seasonal. Lakes could dry up entirely during prolonged droughts. Life there was tougher, more sparse, and often smaller. Survival depended on efficiency rather than abundance. Weather patterns across Pangea were slow but powerful. Without multiple continents to disrupt air circulation, winds traveled long distances uninterrupted. Monsoon-like systems developed along coastlines, bringing intense seasonal rains followed by long, dry periods. Inland dust storms could stretch across regions larger than any modern desert. Time moved differently in this world, not because clocks ticked slower, but because change itself unfolded over immense spans. Species evolved gradually, shaped by pressures that lasted for millions of years rather than generations. Extinction events, when they occurred, were global rather than regional. When conditions shifted, there was often nowhere else to go. Yet life persisted. It adapted, diversified, and experimented. Some lineages failed. Others quietly succeeded, passing traits forward that would later shape the age of dinosaurs, the rise of mammals, and eventually the familiar world outside your window. Pangea was not just a backdrop for life. It was an active force constantly influencing who survived, who thrived, and who vanished. As the supercontinent continued its slow existence, forces deep within Earth were already at work. Heat built beneath the crust. Stresses accumulated. Long before the land began to split apart, subtle changes were already influencing climate, sea levels, and ecosystems. The world of Pangea was never truly still. It only appeared that way when viewed from a human sense of time. When all the land on Earth was joined together, the planet behaved in ways that feel unfamiliar to us now. It wasn't simply a matter of continents touching at their edges. The entire surface of the world functioned as one connected system, where changes in one region could ripple outward across thousands of kilometers of uninterrupted land. Life evolved within that continuity, shaped by distance without division, by climate without moderation, and by time without urgency. Picture standing somewhere deep inland on this ancient Earth. Not near a coast, not close enough to smell salt or hear waves, but surrounded by land in every direction. If you were to walk east or west, north or south, you could travel for months or years without ever encountering an ocean. That sense of endless interior defined much of Pangea's character. Unlike today's continents, which are wrapped in coastlines and shaped by maritime influence, Pangea had a vast core where the sea's stabilizing effect simply could not reach. Because of this, the climate across the supercontinent was extreme. Coastal regions experienced seasonal rains driven by powerful atmospheric circulation, but those rains often faded long before reaching the center. The interior became dry, dusty, and sharply seasonal. Summers could be intensely hot. Winters, depending on latitude and era, could become surprisingly cold. Temperature swings were larger, and weather patterns were slower, often settling into rhythms that lasted decades rather than years. Life adapted to this pace. Plants growing far from the coasts could not rely on frequent rainfall. Many developed thick waxy coatings on leaves to reduce water loss. Roots grew deep, seeking moisture stored far below the surface. Growth tended to be slow but steady, favoring survival over speed. Instead of rapid blooming and fruiting cycles, plants invested energy and durability. The landscape itself reflected this endurance. Wide floodplains formed along massive river systems that drained the interior. These rivers were unlike most modern ones. With no mountain ranges formed by colliding continents to constantly redirect them, many flowed lazily for immense distances, shifting their paths over geological time rather than carving dramatic valleys. During wet seasons, they spilled across flat terrain, depositing nutrients. During dry periods, they shrank back, leaving behind cracked earth and isolated pools. Animals living here had to tolerate scarcity. Many early reptiles that roamed Pangea were built low to the ground, conserving energy. Their metabolisms were slower than those of modern mammals or birds, allowing them to survive long stretches with limited food. Some could retreat into burrows to escape heat or cold, waiting out unfavorable conditions rather than migrating vast distances. Migration itself looked different on a single supercontinent. With no oceans to cross, animals could gradually expand their ranges over generations. A species that originated near one coastline might over millions of years spread across the landmass, without encountering insurmountable barriers. This led to a surprising uniformity in some groups. Fossils of similar reptiles and plants have been found on what are now separate continents. Not because they crossed oceans, but because those oceans did not yet exist. The air above Pangea carried fine dust for long periods. Winds sweeping across dry interior regions picked up sediment and transported it far away, sometimes depositing it thousands of kilometers from its source. This dust influenced soil composition, affecting what plants could grow where. It also altered atmospheric conditions, scattering sunlight and subtly shaping temperature patterns. Even the rhythm of day and night felt different in such an environment. With fewer clouds in dry regions, days were often intensely bright, while nights cooled quickly. Animals became active during specific windows, avoiding midday heat or nighttime cold, depending on their adaptations. This daily cycle repeated endlessly shaped behavior as strongly as seasonal change. The idea of the land as a breathing world comes from these slow, repeating processes. Forests expanded during wetter eras, pushing into regions that had once been barren. When conditions shifted, those same forests retreated, leaving behind open plains or scrubland. Over millions of years, the land seemed to inhale and exhale life. Never abruptly, always gradually. Volcanic activity added another layer of influence. Pangea formed through massive tectonic collisions, and the stresses within Earth's crust didn't simply vanish once the land was assembled. Volcanic eruptions periodically released vast amounts of gas into the atmosphere, including carbon dioxide and sulfur compounds. These gases altered climate on a global scale, sometimes warming the planet, sometimes cooling it. Life responded again by adjusting rather than fleeing. Plants capable of tolerating higher carbon dioxide levels often grew faster and larger. Others struggled and disappeared. Animals adapted their feeding strategies as vegetation changed. Some becoming more specialized, others more flexible. The sense of time experienced by living things during Pangea was shaped by the stability mixed with slow transformation. There were no sudden shifts caused by continental drift, opening new oceans, or isolating populations overnight. Instead, change crept forward. A river slowly shifted course. A forest edge moved a few km over centuries. A population adapted generation by generation, without ever encountering a clear boundary between old and new worlds. This continuity allowed evolutionary experiments to persist longer. Traits that might fail quickly in a fragmented world could survive long enough on Pangea to find their niche. That included early forms of mammal ancestors, small and unassuming creatures that lived in the shadows of large reptiles. Their success did not depend on dominance, but on persistence, flexibility, and the ability to survive when conditions grew harsh. Soundscapes of this world would have been quieter than those of later eras. There were no birds yet, no buzzing insects tied to flowering plants. Instead, the dominant sounds would have come from wind moving across open land, water flowing through broad channels, and the movement of animals through vegetation. Life did not announce itself loudly. It simply continued. Even the night sky would have felt subtly different. With fewer plants releasing oxygen in certain eras, atmospheric composition shifted, affecting how stars appeared. Dust and volcanic aerosols sometimes dimmed the heavens. Other times, clearer skies revealed vast starfields uninterrupted by modern light pollution or dense cloud cover. Through all of this, the land remained joined. No creature living during Pangea would ever experience separation by ocean unless it lived at the very edge of the continent. This unity shaped instincts. There was no inherited fear of vast water barriers, no evolutionary pressure to fly across seas or swim long distances between land masses. That would come later as the world slowly began to pull itself apart. As Pangea persisted, stress accumulated beneath the surface. Heat rose from Earth's mantle, thinning the crust in places. Small rifts formed, barely noticeable at first. To the life above, nothing dramatic seemed to be happening. Forests still grew. Rivers still flowed. Animals still followed familiar paths. Seen from above, Pangea would not have looked like a map we recognize today. There would have been no familiar outlines, no clean separations, no narrow straits or scattered islands to guide the eye. Instead, the planet's surface would have appeared as one immense, irregular landmass, surrounded almost entirely by a single global ocean. The shape was uneven, broad in some regions, narrow in others, with long sweeping curves and deep inland reaches that pushed far away from the sea. From a high vantage point, if such a thing were possible at the time, Earth would have seemed quieter, simpler in structure but heavier in presence. The first thing that would stand out is scale. Pangea covered nearly a third of Earth's surface, far larger than any continent today. Its width spanned vast stretches of latitude, reaching from near the poles down toward the equator. Because of this, it experienced a wide range of climates all at once, from cooler southern and northern regions to warm, often humid equatorial zones. Yet despite this variety, the land still felt unified, like one enormous body rather than a collection of parts. Coastlines existed, of course, but they were fewer and less intricate than modern ones. Today's continents are frayed at the edges, carved by rising and falling sea levels, broken by peninsulas, bays, and island chains. Pangea's coastline was comparatively smooth and continuous. There were gulfs and shallow seas cutting into the land, but they did not fragment it. Large embayments extended inward, creating coastal regions where marine and terrestrial life mixed. But beyond those zones, the land stretched on uninterrupted. From above, color would have varied depending on era and location. Some regions were dark with vegetation, dense forests spreading across lowlands and river systems. Others appeared pale and dusty, vast interior deserts reflecting sunlight. Seasonal shifts could alter these colors gradually. During wetter periods, greens expanded outward from rivers and coasts. During drier stretches, browns and reds reclaimed the land, exposing bare soil and rock. Mountains rose in long chains, where ancient continents had collided to form Pangea. These ranges were not always sharp or jagged. Many had already been worn down by erosion, softened by time and weather. From above, they appeared as long, dark spines or rippled ridges, casting subtle shadows that changed with the sun's angle. These mountains influenced wind patterns, rainfall, and river flow, shaping life far beyond their immediate slopes. Rivers were among the most striking features visible from a high perspective. Without frequent tectonic disruptions, some river systems became enormous, flowing across thousands of km. They branched slowly, forming wide floodplains rather than steep valleys. During rainy seasons, these rivers spread outward, creating temporary wetlands that shimmered under the sun. From above, they looked like veins across the land, carrying water from the interior toward distant seas. The interior of Pangea was where the sense of no edges truly took hold. Standing there or looking down upon it, there was no visual cue that land would ever end. The horizon revealed more of the same terrain stretching endlessly. This vastness affected everything. Winds traveled farther without interruption. Weather systems lingered longer. Heat built up during the day and escaped quickly at night. Life in these regions adapted to endurance rather than abundance. Cloud patterns above Pangea reflected this scale. Large, slow-moving systems dominated over the interior. Skies were often clear for long stretches broken only by distant storms. Along the coasts and near equatorial zones, cloud cover was more frequent, forming seasonal bands that shifted gradually north and south. From above, these clouds traced the breathing rhythm of the planet, expanding and contracting with the seasons. The surrounding ocean, Panthalassa, emphasized the land's unity. It was vast beyond comparison, larger than all modern oceans combined. From above, it wrapped around Pangea like a continuous border, deep and dark, farther from shore, lighter near coastal shallows. There were few island chains, as most volcanic activity occurred along the edges or deep beneath the sea. The ocean felt like a single entity rather than a collection of basins. Sea level changes over time subtly reshaped the coastline. When sea levels rose, shallow inland seas formed, flooding low-lying regions and creating temporary marine environments deep within the continent. When sea levels fell, those seas retreated, leaving behind salt flats, sediment layers, and fossil-rich basins. From above, these changes appeared slow and gentle, almost imperceptible. Over a lifetime, yet transformative over millions of years, vegetation patterns followed water. From the air, forests clustered along rivers, coasts, and wetter regions, forming dark textured patches against lighter surroundings. These forests were not uniform. Some were dominated by tall conifers. Others consisted of dense fern undergrowth. In swampy regions, tree-like plants rose from waterlogged soil. Their remains eventually compressed into coal. The absence of flowering plants gave these landscapes a different texture, more uniform in color, less punctuated by seasonal blooms. Animal movement, if visible, would have appeared subtle and scattered. Large herds, as we know them today, were rare or non-existent during much of Pangea's history. Instead, animals were spread thinly across wide areas, following water sources and vegetation belts. Tracks crossed floodplains, converged at rivers, then vanished into forest cover or open scrub land. Life was present, but it did not dominate the land in the way later eras would. The lack of edges also meant fewer natural barriers. From above, there were no obvious borders dividing ecosystems sharply. Transitions between environments were gradual. Forests thinned into open woodland. Woodlands gave way to grass-like plants or barren ground. These gradients allowed species to adapt slowly as conditions changed rather than facing abrupt limits. Light played a different role in shaping the land's appearance. With fewer clouds in many regions, sunlight was intense. Shadows were sharp at midday, longer and cooler at dawn and dusk. Over deserts, light reflected strongly, heating the air. Over forests and water, it was absorbed, creating microclimates. From above, these contrasts created subtle patterns shifting throughout the day. Volcanic regions added dramatic marks to the surface. Lava flows spread across wide areas during periods of activity, darkening the land. Ash clouds drifted far from eruption sites, settling over forests and plains. Over time, these layers enrich soils, allowing vegetation to return even more vigorously. From a high view, volcanic regions appeared as scars and stains, reminders of the forces beneath the crust. Polar regions of Pangea, while cooler, were not locked in ice as they are today. The planet's climate during many periods was warmer overall. Seasonal snow may have appeared in high latitudes or elevations, but large ice sheets were rare for much of Pangea's existence. From above, the poles were still land, still connected, still part of the same vast whole. One of the most striking aspects of viewing Pangea from above would be the absence of fragmentation. There were no familiar shapes to orient oneself by. No Mediterranean Sea, no Atlantic Divide, no Pacific Rim. Orientation depended on rivers, mountains, and climate bands rather than coastlines. Navigation, for any hypothetical observer, would rely on patterns of land and sky rather than edges. This unity influenced how life spread and diversified. From an aerial perspective, there were no isolated pockets where evolution could take radically different paths without contact. Gene flow across populations was easier. Similar species appeared across wide areas. Endmies, the presence of species found only in one small region, was less pronounced than it would become later. As time passed, subtle changes began to appear. Cracks formed deep below the surface, invisible from above. At first, heat caused the crust to thin in certain regions. Volcanic activity increased along long linear zones. If one could compare views separated by millions of years, faint lines might become visible, marking where the land was under strain. Still, for most of Pangea's existence, these changes were background noise. The dominant impression remained one of continuity. The land rose and fell gently. Rivers shifted. Forests advanced and retreated. Deserts expanded and contracted. All of it happening without the dramatic punctuation of continental separation. This perspective helps explain why life during Pangea developed the way it did. The planet itself encouraged patience. Adaptations that worked well across large areas thrived. Those that depended on narrow conditions struggled. Survival favored flexibility, tolerance, and the ability to endure long periods of relative sameness. The seas that surrounded Pangea were vast, ancient, and strangely quiet in character, especially when compared to the busy compartmentalized oceans we know today. When nearly all the land on Earth gathered into one enormous supercontinent, the water that remained was not pushed aside so much as reorganized into a single dominant presence. This ocean, known to scientists as Panthalassa, covered most of the planet's surface. It was not divided into named basins or bounded by familiar continental margins. It simply existed, wrapping around the land in one continuous global body of water. From the shoreline, the sea would have felt endless. There were no nearby continents beyond the horizon, no island chains breaking the monotony, no narrow passages funneling currents into predictable paths. Waves rolled in from distances so great that their origins were effectively unknowable. Tides still rose and fell, governed by the moon just as they are today. But the shape of the land meant that tidal patterns were often broad and subdued, rather than sharply amplified in enclosed seas. This immense scale gave the supercontinent seas their quiet reputation. Not silent in the literal sense, of course, but slow to change, slow to respond, and slow to circulate. Modern oceans are constantly stirred by the arrangement of continents. Water is squeezed through straits, deflected by coastlines, and redirected by island Rs. During the time of Pangea, much of that complexity simply did not exist. Currents had fewer obstacles, and as a result, they often traveled in wide, looping paths that could persist for thousands of years. The absence of narrow, shallow seas also mattered. Today, continental shelves are rich zones of life, where sunlight penetrates shallow water and nutrients are stirred up from the seafloor. Pangea had shelves, too, but far fewer of them relative to the planet's total ocean area. Much of Panthalassa was deep, dark water, where sunlight faded quickly and life was sparse compared to coastal environments. Along the edges of Pangea, however, the seas were far from empty. Shallow coastal waters supported reefs, algae, shellfish, and early marine vertebrates. These regions changed with sea level fluctuations, sometimes expanding inland to form broad epicontinental seas, and sometimes retreating to expose land. When shallow seas spread over low-lying areas, they created rich marine habitats that could stretch hundreds of km inland. When they withdrew, they left behind layers of sediment packed with fossils. Despite these active coastal zones, the overall character of the ocean remained stable. Water temperatures varied by latitude, but extreme gradients were less common than in modern times. With one dominant ocean, heat was distributed more evenly on a global scale, even if the process was slow. Warm equatorial waters did not easily mix with colder polar waters, but neither were they isolated into separate basins. Over long spans of time, this contributed to a relatively consistent marine climate. Marine life evolved within this stability. Fish, for example, diversified steadily, filling ecological roles that would persist for millions of years. Early sharks appeared already well adapted to open water life. Their streamlined bodies and efficient swimming styles were perfectly suited to long-distance movement in an ocean without barriers. They could roam vast regions without encountering abrupt changes in environment. Other marine reptiles, later famous during the age of dinosaurs, had their evolutionary roots in these seas. Although many of the iconic forms had not yet appeared, the groundwork was laid. Limbs became better suited for swimming. Bodies became more hydrodynamic. These changes were responses to an environment that rewarded endurance and efficiency over specialization. One of the quieter aspects of the supercontinent seas was their chemical character. Ocean chemistry during different periods of Pangea's existence shifted, slowly influenced by volcanic activity, erosion from the land, and biological processes. Rivers carried minerals from the interior into the sea, altering nutrient levels. At times, this supported blooms of marine microorganisms. At other times, nutrient scarcity limited productivity. Oxygen levels in the ocean also varied. In certain areas, deep waters became low in oxygen, creating conditions where only specialized organisms could survive. These anoxic zones did not necessarily spread rapidly or collapse ecosystems overnight. Instead, they formed gradually, persisted, and then retreated as conditions changed. Life adapted by occupying layers of water where oxygen remained sufficient. Sound traveled differently through these ancient seas. Without modern marine mammals, without snapping shrimp or dense schools of fast-moving fish, the underwater world was likely quieter in a literal acoustic sense. The dominant sounds would have come from waves, storms, and geological activity. Volcanic eruptions beneath the sea occasionally sent shock waves through the water, while landslides along continental margins stirred sediment into vast clouds. Storms over Panthalassa could be enormous. With uninterrupted stretches of warm water, cyclonic systems had room to grow and persist. These storms influence coastal ecosystems by stirring nutrients, reshaping shorelines, and periodically flooding low-lying land. Yet even these events were part of long, repeating cycles rather than constant disruption. The deep ocean floor beneath Panthalassa was shaped by slow-moving tectonic processes. Mid-ocean ridges produced new crust, while older crust sank back into the mantle at subduction zones. These processes occurred far from most life and far from the edges of Pangea, making them invisible to anything living on land or near the shore. Over millions of years, however, they influenced sea level and climate by altering the volume of ocean basins. The silence of the supercontinent seas was also ecological, with fewer isolated habitats. Marine species tended to have wide ranges. Endemic species limited to small areas were less common. This reduced the pace of diversification compared to later periods when continents separated and oceans became more compartmentalized. Evolution still occurred, but it unfolded slowly, shaped by subtle pressures rather than sharp boundaries. Plankton, the foundation of marine food webs, responded to these conditions in quiet but significant ways. Microscopic organisms drifted with currents that moved lazily across the globe. Their populations rose and fell with nutrient availability, light levels, and temperature. Over time, their remains settled on the seafloor, forming thick layers of sediment that would later become rock. These sediments tell a story of patience. Layer upon layer accumulated, each representing thousands or millions of years. Fossils embedded within them record long periods of relative stability, punctuated by gradual change. There are few signs of sudden global marine collapse during much of Pangea's tenure, at least compared to later mass extinction events. The connection between sea and land was constant. Rivers did not just deliver water. They carried organic material, minerals, and life itself into the ocean. Coastal ecosystems depended on this steady input. In turn, the sea influenced the land by moderating coastal climates, providing moisture and shaping weather patterns. Yet for all this interaction, the seas rarely intruded deep into the heart of the continent for long periods. When they did, forming inland seas, these were temporary. They expanded during times of the high sea level and retreated when levels fell. Life adapted to these changes, but always with the expectation that the sea's presence was not permanent. As Pangea aged, subtle changes began to disturb this long silence. Tectonic stresses increased. Volcanic activity intensified in certain regions. New rift zones formed along what would one day become separate continents. These changes influenced ocean circulation, altering currents and temperature patterns. At first, these shifts were barely noticeable. The sea still felt vast. The land still felt unified. Marine ecosystems continued their slow rhythms. But beneath the surface, both literally and figuratively, the conditions that had sustained this quiet stability were beginning to shift. Life at the heart of Pangea existed in a space defined less by edges and more by distance. Far from the moderating influence of the sea, far from the relatively stable climates of coastlines, the interior of the supercontinent was a place where extremes ruled quietly and consistently. This was not a landscape of constant catastrophe, but one of tests. Heat lingered, dryness persisted, seasons stretched, and the organisms that lived there were shaped not by sudden change, but by the steady pressure of having to endure. If you could stand somewhere near the center of Pangea during much of its history, the land around you would likely feel open and exposed. Forests did exist, but they were not continuous blankets of green. Instead, wooded regions clustered around reliable water sources or areas where rainfall patterns allowed trees to take hold. Between these patches stretched vast transitional zones, neither true desert nor dense forest, but something in between. These were landscapes of sparse vegetation, scrubby growth, and open ground. Places where life learned to spread out rather than crowd together. Deserts in the interior were real, but they were not always the shifting sand seas we imagine today. Many were dry plains with hard-packed soil, scattered plants, and seasonal rivers that only flowed after rare rains. During dry periods, the land cracked and baked under the sun. During wetter phases, brief bursts of growth followed, greening the surface just enough to support grazing and browsing animals before fatting again. Forests, where they formed, looked different from modern ones. There were no flowering trees, no grasses carpeting the ground, no birds flitting between branches. Instead, tall conifers, seed ferns, and other ancient plant groups dominated. The canopy could be dense in places, but the forest floor was often dim and cluttered with fallen plant matter. Growth was slow, steady, and resilient rather than fast and lush. Between these forests and deserts lay broad ecological gradients. These transitional regions were among the most important environments in Pangea's interior. Here, plants that could tolerate both dryness and occasional moisture thrived. They were flexible in form and function, able to slow their growth during hard times and resume it when conditions improved. Leaves tended to be tough. Water retention mattered. Survival favored plants that could wait. Animals living in these regions mirrored this adaptability. Early reptiles were especially successful here. Their skin reduced water loss, and their eggs did not require standing water to develop. This freed them from the strict limits faced by amphibians, allowing reptiles to occupy land that fluctuated between wet and dry conditions. Many species were small to medium-sized, conserving energy and minimizing resource needs. Movement across the interior was not constant wandering. Animals followed patterns shaped by water availability. Seasonal migrations occurred, but they were slow and predictable, often following river systems or shifting between slightly wetter and drier zones rather than traveling vast distances. Burrowing was common. Retreating underground provided protection from temperature extremes and dehydration, allowing animals to wait out unfavorable conditions. Food webs were simpler than those in coastal or forested areas, but they were not fragile. Plants formed the base, producing modest but reliable energy. Herbivores fed selectively, often on tough fibrous material. Carnivores, in turn, were opportunistic rather than specialized, feeding on whatever prey was available rather than relying on a single species. Insects played a quiet but essential role. Even without flowering plants, insects pollinated certain species, decomposed plant matter, and served as food for larger animals. Some grew large, especially during periods of higher atmospheric oxygen. Others remained small and numerous, filling ecological niches that kept nutrient cycles moving. The interior climate shaped daily life. Days could be intensely hot, especially during dry seasons. Nights cooled quickly, sometimes dramatically. Animals adjusted their activity patterns accordingly. Many were active during cooler morning or evening hours. Others became nocturnal, avoiding daytime heat altogether. This rhythm reduced competition and conserved energy. Rain, when it came, was transformative. Storms could sweep across the interior after long, dry stretches, filling rivers, soaking soil and triggering rapid plant growth. For a brief time, the land felt abundant. Animals fed heavily, reproduced, and expanded their ranges slightly. Then, as moisture faded, growth slowed, and the cycle returned to endurance. These repeating patterns created a sense of predictability. Life did not need to adapt to chaos so much as to repetition. The challenge was not surprise, but persistence. Organisms that could not tolerate long, dry spells, temperature swings, or limited food supplies gradually disappeared from the interior. Those that remained carried traits well suited for restraint. Over millions of years, this environment influenced evolution in subtle ways. Body plans favored efficiency. Excess was a liability. Large size could be advantageous for conserving heat or traveling between resources, but it also increased energy demands. As a result, many successful interior species struck a balance. Large enough to move and compete, small enough to survive scarcity. The interior of Pangea also acted as a filter. Species that evolved along coasts or in wetter regions could spread inland only if they possessed the right traits. Many could not. This limited which lineages became widespread across the supercontinent. Those that passed this filter often became dominant, spreading across vast areas without encountering major barriers. Despite its harshness, the interior was not lifeless or monotonous. It contained variation, nuance, and long-term stability. Different latitudes experienced different seasonal patterns. Some regions were more consistently dry. Others alternated between wet and dry phases over long cycles. Life adjusted locally, creating regional differences even within an overall unified landscape. Fire likely played a role as well. Dry conditions and abundant plant material created the potential for wildfires. These fires reshaped vegetation, cleared old growth, and opened space for new plants. Over time, some species adapted to survive or even benefit from fire, regenerating quickly afterward. Fire added another slow-moving force shaping life without constant destruction. The absence of grasslands, as we know them today, is worth noting. Grasses had not yet evolved, meaning open areas were dominated by low-growing plants, shrubs, and hardy seed plants. This affected how herbivores fed and moved. Grazing in the modern sense did not exist. Instead, animals browsed selectively, feeding on available plant parts rather than sweeping across fields. Water sources acted as hubs of activity. Rivers, lakes, and seasonal wetlands concentrated life. Around them, forests thickened, animal tracks converged, and interactions intensified. These zones were vital for reproduction, feeding, and shelter. Yet they were also vulnerable. Changes in climate or river flow could transform a lush area into a dry one over time, forcing life to adapt again. The interior of Pangea fostered patience. Generations passed under similar conditions with gradual change, rather than abrupt upheaval. Evolution here was shaped by consistency, by the quiet pressure of having to make do with what the land offered year after year, millennium after millennium. As tectonic forces continued their slow work beneath the surface, subtle changes began to ripple through the interior. Volcanic activity altered atmospheric composition. Slight shifts in elevation affected rainfall patterns over immense spans of time. These influences nudged deserts outward or allowed forests to reclaim ground. Life responded as it always had, not with sudden leaps but with incremental adjustments. Species ranges shifted. Some lineages declined, others expanded. The balance between desert and forest never stayed fixed, but it never swung wildly either. It oscillated gently, breathing in and out across the land. Long before flowering plants added color and scent to the land, before bird song filled the air or grass softened the ground, Earth's forests followed a very different set of rules. During the long age of Pangea, forests were older in spirit, slower in growth, and built from forms that feel almost unfamiliar today. These were landscapes shaped by repetition and patience where height mattered, light mattered, and survival depended on mastering both over spans of time that stretched far beyond any single lifetime. Walking into one of these ancient forests would have felt like entering a world, still experimenting with what a forest could be. The first impression would not be flowers or fruit, because neither existed yet. Instead, there would be layers of green and brown arranged in vertical space. Tall trunks rose upward, some straight and column-like, others thick and branching low to the ground. Above them, fronds and needle-like leaves formed canopies that filtered sunlight rather than blocking it completely. Below, the ground was cluttered with fallen plant matter, spores, and decaying wood, creating a soft, uneven surface underfoot. Giant ferns were among the most recognizable features of these forests. Some stood as tall as modern trees, their fronds spreading outward like enormous fans. Unlike modern ferns, which are often understory plants, these ancient forms claim the upper levels of the forest, competing directly for sunlight. Their success came from abundance rather than speed. They produced vast numbers of spores, releasing them into the air in clouds that drifted across the landscape, settling wherever conditions allowed growth. These forests thrived most successfully during periods when the climate was warm and moisture was relatively abundant. Along river systems, floodplains, and low-lying regions near coastlines, forests expanded outward, sometimes covering enormous areas. The soil in these regions was often waterlogged, especially during earlier phases of Pangea's history. Trees and ferns adapted to these conditions with shallow root systems and trunks capable of tolerating prolonged saturation. In these wet forests, growth was steady and dense. Plant matter accumulated faster than it could decay, especially in low-oxygen soils. Over time, layers of dead vegetation built up, compressing under their own weight. These layers would eventually become coal deposits, though at the time they simply formed thick, spongy ground that absorbed water and muffled sound. Walking through such a forest would have felt quiet, the air heavy and still, broken only by wind moving through leaves or the distant movement of animals. Not all forests were swampy. As Pangea evolved and climates shifted, drier forests became more common, especially farther inland. These forests were dominated by seed plants such as conifers and cycad. Their leaves were tougher, better suited to conserving water. Their reproductive strategies relied less on water and more on wind, an advantage in regions where rainfall was unpredictable. Height became a crucial factor in these environments. Taller plants captured more sunlight, shading out competitors below. This created a vertical hierarchy that shaped the entire ecosystem. Light filtered downward unevenly, creating patches of brightness and shadow. Plants adapted by specializing. Some grew tall and sturdy. Others remained low, thriving in dimmer conditions. This division of space allowed more life to coexist than would otherwise be possible. The phrase "first all shadows" captures something important about this period. These forests were among the earliest environments on Earth where height consistently shaped survival. Shadows cast by towering plants created cooler, more stable microclimates beneath them. This benefited certain animals and plants while excluding others. Temperature differences between sunlit clearings and shaded areas could be significant, influencing where species fed, rested, or reproduced. Animals inhabiting these forests were still relatively modest in size, but they interacted with the environment in increasingly complex ways. Early reptiles moved through the undergrowth, feeding on insects and small animals. Amphibians remained tied to wetter areas, breeding in pools and slow-moving streams. Insects were abundant, filling the air and soil with activity. Some climbed trees, others fed on decaying plant matter, playing a critical role in nutrient cycling. Without birds or mammals to disperse seeds or spores deliberately, forests relied on wind, water, and chance. This led to dense local populations of certain plants, with long periods of relative stability. When disturbances occurred, such as floods, droughts, or fires, they opened space for new growth. These events did not happen constantly, but when they did, they reshaped forest structure for centuries. Fire deserves special attention. In dry periods, especially in drier forests and transitional zones, fires could sweep through vegetation. These fires were not necessarily frequent, but they were influential. Some plants were better adapted to survive or recover from fire, sprouting anew from roots or releasing spores after heat exposure. Fire cleared dead material, returned nutrients to the soil, and prevented any single species from dominating indefinitely. Over long spans of time, these processes gave forests a dynamic but steady character. They were not static walls of trees. They expanded, thinned, shifted, and reassembled themselves gradually. One area might remain forested for millions of years, while another oscillated between forest and open land, depending on climate patterns. The absence of flowering plants meant that forests lacked many of the visual cues we associate with modern woodlands. There were no bright blossoms, no fruiting seasons marked by color changes. Instead, variation came from structure and texture. Different leaf shapes, trunk forms, and growth patterns created subtle diversity. Seasonal changes still occurred, but they were quieter, expressed through growth rates and leaf shedding rather than dramatic displays. These forests also influenced the atmosphere. Large-scale plant growth drew carbon dioxide from the air and released oxygen. During certain periods, oxygen levels rose significantly, enabling larger insects and influencing animal metabolism. The forests were not just passive scenery. They actively shaped the planet's chemistry, altering conditions for all life. Shadows within these forests carried ecological weight. Cooler, darker areas slowed evaporation, preserving moisture. Animals used these zones for shelter. Plants adapted to low light thrived beneath taller neighbors. This vertical complexity was a major evolutionary step, allowing ecosystems to pack more life into the same area without exhausting resources. Over time, forest edges became important zones of interaction. Where forest met open land, light and temperature gradients created opportunities. Some species specialized in these edges, benefiting from access to both environments. These transitional areas were often rich in life, even if they covered less area than forests themselves. As Pangea continued its slow existence, the distribution of forests shifted with changing climate and geography. When conditions became drier overall, forests retreated toward coasts and river systems. When wetter periods returned, they expanded again. This back-and-forth movement influenced which species survived and which faded away. The long persistence of these ancient forests left a deep imprint on life. Traits that allowed plants to grow tall, tolerate shade, and reproduce without animals became widespread. Animals adapted to navigating dense vegetation, climbing, burrowing, and hiding. These adaptations would later prove useful, as new types of forests emerged with the rise of flowering plants. These forests did not know they were ancient or transitional. They simply existed, casting their tall shadows across a world that had not yet learned how to be divided. Long before dinosaurs became the dominant figures of prehistoric life, before their names filled textbooks and museum halls, the land of Pangea already belonged to reptiles. These earlier reptiles did not roar across open plains or tower above forests. Their rule was quieter, slower, and far more foundational. They were the first vertebrates to truly free themselves from constant dependence on water. And in doing so, they reshaped what life on land could be. To understand why reptiles mattered so much during this time, it helps to remember what came before them. For hundreds of millions of years, amphibians had been the primary large animals on land. They thrived in moist environments close to rivers, swamps, and coastal wetlands. Their skin absorbed water easily, and their eggs required damp conditions to survive. This worked well in a world dominated by swampy forests and frequent rainfall. But as Pangea formed and its vast interior grew drier, those rules became limiting. Reptiles brought a different solution. Their skin was tougher and less permeable, reducing water loss. Their eggs were encased in protective shells, allowing embryos to develop on dry land rather than in water. This single innovation, often overlooked, was revolutionary. It meant reproduction was no longer tied to ponds or streams. It allowed reptiles to push farther inland than any vertebrates before them, colonizing regions that amphibians could not reliably survive in. These early reptiles were not a single uniform group. They represented a broad range of forms, lifestyles, and strategies. Some were small lizard-like animals that darted through undergrowth or across open ground, feeding on insects and small prey. Others were larger, heavier body creatures that moved more deliberately, browsing on vegetation or ambushing prey. What united them was not appearance, but adaptability. The interior of Pangea offered few guarantees. Water sources were scattered. Food availability fluctuated with seasons that could last for years. Temperatures swung between extremes. Reptiles thrived here not because they were faster or stronger than their competitors, but because they were efficient. Many had slower metabolisms than later warm-blooded animals, allowing them to survive on less food. They could go longer between meals. They could wait. Burrowing behavior became common. Digging into soil provided shelter from heat during the day and cold at night. Burrows also offered protection from predators and a stable environment for resting or laying eggs. Some species likely spent large portions of their lives underground, emerging only when conditions were favorable. Diet among these reptiles varied widely. Herbivorous species fed on tough, fibrous plants that dominated Pangea's landscapes. Without grasses or flowering plants, vegetation was often harder to digest. This pushed herbivores to evolve specialized teeth and jaw structures capable of processing leaves, stems, and seed-bearing structures. Carnivorous reptiles, meanwhile, hunted smaller animals, including other reptiles, amphibians, and abundant insects. Predation during this time did not rely on speed alone. Many predators were ambush hunters using camouflage and patience. Forest edges, river banks, and transitional zones between open land and vegetation were prime hunting grounds. Here, prey moved predictably between food and water, allowing predators to wait rather than chase. The absence of dinosaurs did not mean the absence of dominance. Certain reptile groups filled roles similar to those dinosaurs would later occupy. Large predators existed, though they were fewer and often less specialized. Their success depended on being generalists, capable of switching prey when conditions changed. Social behavior among these reptiles remains difficult to reconstruct, but evidence suggests it was limited. Most species likely lived solitary lives or formed loose, temporary groupings around resources. The environment favored self-sufficiency. Dependence on group cooperation would have been risky in a world where food and water could not be guaranteed. Growth rates were slow. Many reptiles took years to reach maturity. This slow pace matched the rhythm of their environment. There was little advantage to rapid growth if resources were unpredictable. Longevity rather than speed offered a better chance of reproducing successfully over time. The relationship between reptiles and plants was indirect but important. As herbivores fed, they influenced vegetation patterns, preventing any single plant species from overwhelming others. Their movement spread spores and seeds, incidentally shaping plant distribution. Carnivores, by controlling herbivore populations, further influenced how vegetation grew. Climate shifts during Pangea periodically altered which reptile groups thrived. During wetter periods, amphibians could temporarily reclaim territory, competing with reptiles in certain regions. But as dryness returned, reptiles regained their advantage. This back-and-forth competition refined traits over millions of years, pushing reptiles toward greater efficiency and resilience. One of the most significant evolutionary developments during this time was the early branching of reptile lineages that would later give rise to dinosaurs, mammals, and modern reptiles. These lineages were not yet distinct in the way we recognize today, but their differences were already forming. Subtle changes in skull openings, limb posture, and metabolism set them on diverging paths. Some reptiles began to adopt a more upright stance, lifting their bodies slightly off the ground rather than sprawling fully to the sides. This posture improved breathing efficiency during movement and allowed for more sustained activity. At the time, it was just one of many variations, not yet a defining advantage. Later, it would become crucial. Others experimented with different feeding strategies, tooth shapes, and body proportions. Evolution during this era was not driven by sudden innovation, but by gradual refinement. Traits that worked slightly better under Pangea's conditions persisted. Those that didn't faded quietly. The sensory world of these reptiles was also changing. Vision improved in some groups, aiding hunting and navigation across open landscapes. Smell likely played a major role as well, helping animals locate food, recognize territory, or detect predators. Hearing, while present, was probably less developed than in later animals, especially in open environments where sound carried unpredictably. Reptiles occupied nearly every terrestrial niche available at the time. From river banks to forest interiors, from semi-arid plains to wetter lands, they formed the backbone of land-based ecosystems. Without them, the interior of Pangea would have been far emptier, its harsh conditions limiting life to scattered pockets. Extinction events did occur during this long period, sometimes dramatically reducing reptile diversity. Volcanic activity, climate shifts, and changes in sea level could all disrupt ecosystems. Yet reptiles repeatedly rebounded. Their flexibility allowed surviving species to spread into newly available niches, reshaping communities without fundamentally altering the overall balance. As time passed, certain reptile groups began to show traits that hinted at future dominance. Faster growth rates, more efficient movement, improved respiratory systems. These changes did not immediately elevate them above others, but they prepared the groundwork for what would come later. Importantly, dinosaurs did not appear suddenly into an empty world. They emerged into landscapes already shaped by millions of years of reptile adaptation. The strategies dinosaurs would later use, such as efficient locomotion and diversified diets, were refinements of patterns established long before the world reptiles ruled before dinosaurs was not inferior or incomplete. It was simply different. It valued endurance over spectacle, stability over speed. Life unfolded at a pace that matched the slow breathing of the supercontinent itself. As Pangea continued to exist, pressures accumulated. Environments shifted. New competitors emerged. Some reptile lineages declined, unable to adapt quickly enough. Others continued to experiment, subtly altering form and function with each generation. Those experiments would eventually lead to a turning point, one that did not erase the earlier reptiles, but built upon their legacy. The land was already prepared, the ecosystems were already structured, and the rules of survival written during this long age of reptile dominance would continue to shape life even as new rulers stepped into the open spaces they left behind. Insects were already ancient long before Pangea finished assembling itself, but the world they inhabited during the height of the supercontinent allowed them to reach forms, sizes, and levels of success that feel almost unreal today. While large reptiles moved slowly across plains and forests grew in patient silence, insects filled the spaces in between. They crept, crawled, burrowed, and flew through nearly every environment Pangea could offer, quietly becoming one of the most influential groups of organisms the planet had ever known. To picture insect life during this time, it helps to let go of modern expectations. There were no bees drifting between flowers, no butterflies marking seasons with color, no ants farming aphids or building towering colonies. Flowering plants had not yet appeared, and with them absent, the insect world followed very different rules. Yet this did not limit insects. In many ways, it freed them. The unified land mass of Pangea created enormous stretches of connected habitat. For insects, this continuity was an advantage. Species could spread gradually across vast areas without encountering oceans or abrupt ecological barriers. Over long periods, populations expanded, mixed, and adapted to regional conditions while remaining part of a much larger whole. This helped successful body plans persist and refine themselves rather than fragmenting into isolated forms. Atmospheric conditions played a major role in shaping insect life. During several periods of Pangea's history, oxygen levels were significantly higher than they are today. Insects breathe through a network of tubes that deliver oxygen directly to their tissues, a system that works best when oxygen is abundant. Higher oxygen allowed insects to grow larger without suffocating under their own size. As a result, some insects reach proportions that seem exaggerated by modern standards. Dragonfly-like insects, with wingspans approaching that of a small bird, glided through forest air. Millipedes grew longer and thicker than any living today, moving slowly through leaf litter and decaying wood. These giants were not monsters in behavior. They followed the same basic instincts as their smaller relatives, feeding, reproducing, and avoiding danger. Their size was a reflection of opportunity rather than aggression. Not all insects were large. In fact, most remained small, numerous, and highly specialized. Beetles, early cockroach relatives, and primitive grasshopper-like insects filled the soil, leaf litter, and vegetation. They fed on plant material, fungi, and decaying matter, breaking down organic material and returning nutrients to the soil. Without them, forests would have choked under their own debris. Insects were the primary decomposers on land. Bacteria and fungi played important roles, but insects accelerated the process, shredding plant material into smaller pieces and spreading microbes through their movement. This recycling was essential in Pangea's forests, where plant growth could be dense and decay slow, especially in wetter regions. Flight gave insects a unique advantage in a world without birds. The air above forests and plains belonged to them alone. Flying insects could travel between habitats, escape predators, and locate new food sources with relative ease. Wind patterns over the supercontinent influenced where insects could go, sometimes carrying them far from their original homes. Over generations, this passive dispersal helped spread species widely. Reproduction among insects was prolific. Many species produced large numbers of offspring, knowing that only a fraction would survive. This strategy worked well in an environment where conditions could fluctuate. When resources were abundant, populations exploded. When conditions worsened, numbers dropped without driving species to extinction. This resilience made insects one of the most stable components of Pangea's ecosystems. Insects interacted with plants in ways that predate pollination as we know it. Some fed on spores, seeds, or leaves. Others lived within plant tissue, boring tunnels or laying eggs. These interactions influence plant evolution, selecting for tougher leaves, chemical defenses, or growth patterns that minimize damage. Even without flowers, plants and insects were already shaping each other's futures. Predation on insects was widespread. Was reptiles, amphibians, early synapsids, and even other insects fed on them. This pressure encouraged a variety of defenses. Hard exoskeletons protected against bites. Camouflage helped insects blend into bark, leaves, or soil. Some developed warning colors, signaling toxicity or unpleasant taste. Others relied on sheer numbers to overwhelm predators' ability to consume them all. Sound was part of this world, though it would not resemble the insect chorus of modern summers. Some insects produced vibrations or noises by rubbing body parts together. But the absence of flowering plants and birds meant the soundscape was different. The buzz of wings, the rustle of movement through vegetation, and the occasional chirp would have been present, but often subtle and localized. Night transformed insect activity. With temperatures dropping and larger predators less active, many insects emerged after sunset. Nocturnal behavior reduced competition and predation, allowing species to exploit resources safely. The absence of artificial light meant darkness was complete, guided only by moonlight and stars. Insects navigated using cues we're only beginning to understand, including polarized light and subtle environmental gradients. Seasonality shaped insect life cycles. In regions where wet and dry seasons alternated, insects synchronized reproduction with favorable conditions. Eggs could lie dormant through harsh periods, hatching when moisture returned. Some species completed their entire life cycle quickly, taking advantage of brief windows of abundance. Others lived longer, slower lives, feeding and growing over extended periods. Inland regions of Pangea posed challenges. Dryness limited insect diversity compared to wetter zones. But those that survived were highly adapted. Thick exoskeletons reduced water loss. Burrowing behavior provided refuge from heat. Feeding habits shifted toward hardy plants or detritus that persisted even during dry spells. These insects were not abundant, but they were persistent. In wetter forested areas, insect diversity flourished. Here, layered vegetation provided numerous niches. Some insects lived high in the canopy, feeding on leaves or spores. Others occupied understory plants or the forest floor. This vertical separation reduced competition and allowed many species to coexist in the same area. The absence of flowering plants also meant insects did not yet form the tight mutualistic relationships that would later define ecosystems. They were not bound to specific plants for survival. This independence allowed them to adapt more flexibly to changing conditions, spreading wherever resources appeared. Over millions of years, insects diversified into countless forms, experimenting with body shapes, feeding strategies, and behaviors. Many lineages that exist today trace their origins back to this time. Others flourished briefly and then vanished, leaving only fossils behind. The overall trend, however, was expansion and refinement rather than boom and collapse. Environmental disruptions affected insects as well. Volcanic eruptions altered climate and air quality. Changes in oxygen levels influenced body size. Shifts in vegetation reshaped habitats. Insects responded quickly compared to larger animals, adjusting population sizes and distributions within relatively short time scales. This responsiveness made them early indicators of environmental change. Insects also influenced soil formation. Their borrowing air raided the ground, improving water penetration and root growth. Their waste added organic matter. Over time, these small actions contributed to the development of soils capable of supporting larger plants. In this way, insects quietly engineered the land beneath their feet. The unity of Pangea meant that insect communities were less isolated than they would later become. This reduced extreme specialization, but encouraged broad adaptability. Insects that could tolerate a range of conditions thrived. Those that depended on narrow niches were more vulnerable to long-term change. As the supercontinent aged, subtle shifts began to alter insect life. Climate zones moved. Forests expanded and contracted. New plant types emerged. Insects followed these changes, some declining, others evolving new strategies. The groundwork was being laid for the explosive diversification that would come with the rise of flowering plants and the breakup of Pangea. Yet during this long unified phase, insects already dominated in ways that often go unnoticed. They outnumbered all other land animals combined. They influenced plant growth, soil health, and nutrient cycles. They fed countless predators and shaped evolutionary pathways across ecosystems. Their presence was constant, but rarely dramatic. They did not build monuments or leave obvious traces visible from afar. Instead, they worked at small scales, moment by moment, generation by generation. In doing so, they helped sustain life across a continent-sized world. Along the edges of Pangea, where the immense land mass finally gave way to water, the planet entered a different rhythm. Here, the influence of the sea softened extremes, moderated temperature, and introduced a slow but constant movement that contrasted with the stillness of the interior. These coastal margins and surrounding oceans were not secondary to life on the supercontinent. They were essential, shaping evolution in ways that would echo long after Pangea itself was gone. The dominant ocean surrounding the land was vast beyond modern comparison. Panthalassa stretched uninterrupted around the supercontinent, a single global body of water whose size dwarfed today's Pacific. It was deep, old, and patient. Water circulated slowly through it, driven by wind, temperature differences, and the gradual rotation of the planet. Without multiple continents to interrupt currents, circulation patterns were broad and long-lived. Change happened, but it happened gradually. Where Pangea met this ocean, coastlines formed long, sweeping boundaries. Some were rugged, shaped by tectonic uplift and erosion. Others were low and shallow, sloping gently into the sea. These shallow margins were especially important. Sunlight could penetrate the water here, allowing photosynthetic life to flourish. Algae, early plankton, and reef-building organisms formed the base of rich marine ecosystems. Unlike modern coastlines, which are broken by bays, islands, and continental shelves of varying widths, Pangea's edges were often simpler. This simplicity did not mean a lack of life. It meant that marine habitats extended in long, continuous bands. Species could spread laterally along coastlines for enormous distances without encountering major barriers. This connectivity shaped marine evolution, favoring organisms that could thrive across wide ranges. Reefs existed during the time of Pangea, though they were built by organisms different from those that dominate reefs today. Modern coral reefs rely on stony corals and complex symbiosis with algae. In earlier eras, reefs were often constructed by sponges, algae, and other reef-forming creatures that built rigid frameworks from calcium carbonate. These reefs created structure in shallow seas, offering shelter and feeding grounds for countless species. Fish were already diverse and well established in these waters. Both cartilaginous fish, such as early sharks and bony fish, occupied a variety of ecological roles. Sharks, in particular, were well suited to the open ocean. Their streamlined bodies and efficient swimming allowed them to patrol vast areas. They were not mindless predators, but adaptable hunters capable of feeding on many different prey types depending on availability. Bony fish explored a wide range of forms. Some were small and agile, living in schools near reefs or along coastlines. Others grew larger, venturing into deeper water. Fins adapted for maneuverability or endurance depending on lifestyle. These fish laid the groundwork for the incredible diversity that would later emerge in more fragmented oceans. Marine invertebrates were abundant and varied. Mollusks, including early relatives of clams, snails, and squid, thrived along the seafloor and in open water. Some burrowed into sediment, filtering food particles from the water. Others grazed on algae growing on rocks and reefs. Their shells provided protection, and after death contributed to the buildup of marine sediments. Cephalopods deserve special mention. Ancient relatives of modern squid and octopus already displayed remarkable intelligence and adaptability. Some possessed long, straight shells that helped regulate buoyancy, allowing them to move vertically through the water column. These animals were active predators using speed and sensory awareness rather than brute force. Plankton formed the invisible foundation of ocean life. Microscopic algae captured sunlight and converted it into energy, supporting everything above them. Zooplankton fed on these algae and in turn became food for larger animals. In the vastness of Panthalassa, plankton populations rose and fell with nutrient availability, temperature, and light. Their remains slowly settled to the seafloor, forming thick layers of sediment. Over time, ocean chemistry during the Pangea era changed slowly but significantly. Volcanic activity released gases into the atmosphere, which dissolved into seawater. Rivers carried minerals from the land into the sea. These inputs altered nutrient levels and oxygen availability. At times, deeper waters became low in oxygen, creating zones where only certain organisms could survive. These conditions did not appear suddenly, but developed over long periods, shaping which species thrived and which declined. Marine reptiles began to appear during this time, though they were not yet the iconic forms of later eras. Early experiments in returning to the sea involved reptiles adapting limbs into paddles, developing streamlined bodies, and altering breathing strategies. These animals demonstrated that the boundary between land and sea was not fixed. Life could move between realms when conditions allowed. The edges of Pangea were dynamic environments. Sea levels rose and fell over geological time, flooding low-lying areas and then retreating. When shallow seas spread inland, they created temporary marine habitats rich in life. When they withdrew, they left behind sediments and fossils that recorded these changes. Coastal ecosystems had to adapt repeatedly. But because change was gradual, many species managed to persist through shifting conditions. Storms played a major role along these coasts. With long stretches of uninterrupted ocean, storms could grow large and powerful. They churned surface waters, mixing nutrients from deeper layers and triggering bursts of biological productivity. Storms also reshape shorelines, eroding cliffs, depositing sand, and altering habitats. For marine life, storms were disturbances, but also opportunities. Temperature gradients in the ocean influenced species distribution. Equatorial waters were warmer and supported different communities than cooler, higher latitude regions. However, because there was only one major ocean, these gradients were smoother than today's sharp contrast between separate basins. Species ranges were often broad, extending across multiple climate zones. Sound in these oceans was muted compared to modern seas. There were no whales calling across distances, no snapping shrimp crackling constantly. The dominant sounds came from waves, storms, and geological events. This quieter acoustic environment influenced how animals sensed their surroundings. Vision and chemical cues were more important than sound for communication and hunting. The interaction between land and sea was constant. Rivers delivered nutrients that fueled coastal productivity. In turn, marine organisms influenced land by shaping coastlines and contributing sediments. Dead marine life accumulated along shores, providing food for scavengers and enriching soils. The boundary between terrestrial and marine ecosystems was porous and active. Despite this richness, much of Panthalassa remained sparsely inhabited. The deep open ocean offered fewer resources than coastal zones. Life existed there, but at lower densities. Survival depended on efficient use of scarce food and the ability to travel long distances. This favored streamlined forms and slow, steady lifestyles. Evolution in these oceans favored resilience. Species that could tolerate changes in temperature, oxygen levels, and food availability thrived. Specialization existed, but extreme specialization was risky in such a vast, interconnected environment. Generalists often had the advantage. As Pangea persisted, subtle tectonic changes began to alter oceanic conditions. Rifting along the supercontinent's margins created new shallow seas and altered circulation patterns. Volcanic activity increased in some regions, changing water chemistry. These shifts introduced new selective pressures, prompting further adaptation. Marine life responded by diversifying. New forms appeared. Others faded away. The overall structure of marine ecosystems remained stable, but details changed. This slow evolution set the stage for later explosions of diversity, when continents separated and new oceans formed. The oceans around Pangea's edges were not merely borders. They were engines of life, shaping climate, chemistry, and biology on a global scale. Creatures living within them were part of a system that connected land and sea into a single functioning planet. On a planet shaped into a single immense landmass, the idea of seasons took on a very different meaning. Without the familiar pattern of continents broken by oceans, bays, and islands, weather did not reset itself quickly. It lingered. It settled in. It unfolded over spans of time that made a single year feel insignificant. At the height of Pangea's existence, seasons were not just recurring changes. They were extended states of being, sometimes lasting decades, sometimes centuries, shaping life with patience rather than urgency. To understand how weather worked on Pangea, it helps to begin with what was missing. There were far fewer coastlines than there are today, and those coastlines were often distant from the interior. In the modern world, oceans act as enormous regulators. Water absorbs heat slowly and releases it slowly, softening temperature extremes and feeding the atmosphere with moisture. On Pangea, much of the land lay far beyond that moderating reach. The result was a climate system dominated by land behavior rather than ocean behavior. In the interior, summers could become intensely hot. With little nearby water to absorb solar energy, the ground heated quickly and held that heat. Air temperatures climbed and remained high for long stretches. Nights cooled more rapidly, but daytime heat returned relentlessly. Winters, by contrast, could bring pronounced cooling, especially at higher latitudes or elevations. These seasonal contrasts were sharper than those experienced in many modern regions. Rainfall patterns reflected this imbalance. Moisture entering the atmosphere came mostly from the ocean edges. Winds carried that moisture inland, but as air masses traveled farther over land, they lost water through precipitation. By the time they reached deep interior regions, little remained. As a result, large areas experienced prolonged dryness punctuated by infrequent, but sometimes intense rainfall events. These events mattered greatly. When rain finally arrived after a long dry period, it could fall heavily, saturating soil quickly and triggering sudden growth. Rivers swelled. Plants responded almost immediately, producing leaves and spores. Animals emerged from shelters to feed and reproduce. Then, as moisture faded, activity slowed again. Life learned to operate in pulses rather than steady flows. Seasonal cycles were influenced strongly by latitude. Near the equator, temperature variation across the year was smaller, but rainfall patterns could be extreme. Monsoon-like systems developed along coastal regions and extended inland during certain periods. These systems were driven by the differential heating of land and ocean, creating powerful seasonal winds that reversed direction as conditions changed. When monsoons arrived, they reshaped landscapes. Dry plains transformed into wetlands. Rivers carved new channels. Sediment spread across floodplains. When monsoons retreated, those same areas dried, leaving behind nutrient-rich soils that supported new growth. Over time, these repeating cycles built complex ecosystems adapted to dramatic seasonal contrast. Farther from the equator, seasons expressed themselves more through temperature than rainfall. Long summers brought warmth and growth. Long winters slowed metabolism and limited activity. Snow and ice appeared in some regions during colder periods, though large permanent ice sheets were uncommon during much of Pangea's history due to overall warmer global temperatures. What made Pangea seasons especially distinctive was their duration. Climatic patterns were not easily disrupted by shifting ocean currents, or rapidly changing sea levels. Without fragmented continents, atmospheric circulation followed stable, large-scale paths. This stability meant that once a region settled into a particular climatic regime, it could persist for extraordinarily long periods. For organisms living on Pangea, this predictability was both a challenge and an advantage. Adaptation favored those that could endure extended conditions rather than respond quickly to short-term change. Plants evolved growth strategies that conserved resources. Animals timed reproduction to align with long, favorable windows rather than brief seasonal peaks. Weather systems themselves moved slowly. Storms over land could persist, especially when fueled by heat accumulated over large areas. Conversely, droughts could extend across regions larger than modern countries, lasting generations. These were not sudden disasters, but drawn-out tests that gradually filtered which species could survive. Wind patterns were powerful and far-reaching. With few obstacles to disrupt airflow, winds traveled long distances across open land. Dust storms became a defining feature of some interior regions. Fine particles lifted from dry soil remained suspended, traveling hundreds or thousands of km before settling. These dust deposits altered soil chemistry far from their source, influencing plant growth and nutrient availability. Dust also affected the atmosphere. It scattered sunlight, sometimes cooling the surface slightly, sometimes altering cloud formation. Over long periods, this contributed to subtle but persistent climate feedbacks. Life adapted to hazier skies and reduced light intensity in some regions, especially during prolonged dry phases. Volcanic activity added another layer of complexity. Pangea formed through massive tectonic collisions, and internal stresses continued long afterward. Volcanic eruptions released gases such as carbon dioxide and sulfur compounds into the atmosphere. Depending on scale and frequency, these gases could warm the planet or trigger temporary cooling. When volcanic activity was sustained over long periods, global climate shifted. Increased carbon dioxide raised temperatures and altered rainfall patterns. Forests expanded into regions previously too dry. In other cases, volcanic aerosols reflected sunlight, cooling the surface and stressing ecosystems. These changes unfolded slowly, but their effects were global. Because change was gradual, ecosystems had time to respond. Species ranges shifted rather than collapsing outright. Some plants retreated toward wetter zones. Others expanded during warmer phases. Animals followed food and water, adjusting movement patterns over generations rather than lifetimes. The absence of frequent climatic resets meant that evolutionary pressures remained consistent. Traits that worked well under prevailing conditions were reinforced over long spans. There was little incentive for rapid innovation. Instead, small advantages accumulated, shaping lineages slowly and steadily. The concept of a year held less significance for many organisms. Life cycles were often tuned to multi-year or even multi-dead patterns. Reproduction might occur only during particularly favorable stretches. Dormancy was common with seeds, eggs, or entire organisms waiting patiently through unfavorable conditions. Insects exemplified this strategy. Many species laid eggs capable of surviving extended dryness. These eggs hatched only when moisture returned. Population booms followed, then receded, leaving behind the next generation prepared to wait again. This rhythm matched the slow breathing of the climate. Larger animals adjusted behaviorally. Burrowing provided refuge from both heat and cold. Some species reduced activity during extreme seasons, conserving energy. Others migrated locally, shifting between slightly different environments rather than undertaking long-distance journeys. Forests responded structurally. Tree growth rings from this era preserved in fossilized, would show evidence of prolonged stress periods followed by recovery. Growth was not uniform year to year, but clustered around favorable intervals. These patterns record climate history in wood rather than ice. Weather also influenced fire regimes. Extended dry periods increased the likelihood of wildfires. When fires occurred, they could spread widely, reshaping vegetation over large areas. Yet fires were not constant. They arrived after long preparation, then passed, allowing ecosystems to recover gradually. Rainfall following fires often triggered rapid regrowth. Some plants were well adapted to this cycle, regenerating quickly after disturbance. Over time, fire became another predictable force rather than a chaotic one. The edges of Pangea experienced more moderated seasons. Coastal areas benefited from nearby water, which tempered temperature swings and provided more reliable moisture. Here, seasonal changes were gentler, though still influenced by large-scale atmospheric patterns. These regions supported richer and more diverse ecosystems, acting as refugees during harsh interior conditions. As tectonic forces slowly began to stretch the supercontinent, subtle changes appeared in climate patterns. New rift zones altered topography. Shallow seas formed in low-lying areas, introducing new sources of moisture. Over time, these changes would break the long-standing stability of Pangea's climate system. Yet for most of its existence, Pangea's weather was defined by endurance rather than surprise. Seasons did not rush past. They settled in, shaped the land, and moved on only when the planet itself shifted course. Life adapted accordingly, learning to wait, conserve, and persist. This way of living left a deep imprint on evolution. Species forged under such conditions carried forward a tolerance for variability and patience. When the world eventually fragmented and climates became more dynamic, those traits would prove valuable. Long before mammals became familiar shapes in the world, before fur, warm blood, and alert eyes defined life on land, their ancestors already existed as quiet participants in the ecosystems of Pangea. They did not dominate landscapes or command attention. Instead, they moved carefully through the margins, leaving faint traces in dust, soil, and time itself. These early mammal ancestors lived in a world shaped by reptiles, harsh climates, and long environmental rhythms, and their survival depended on remaining adaptable, unobtrusive, and patient. These creatures belong to a broad group known as synapsids, a lineage that would eventually give rise to mammals. At the time, they were not yet what we would recognize as mammals. They lacked fur as we know it. Their metabolism was not fully warm-blooded, and their behavior was still shaped by older reptile-like traits. Yet within them were the beginnings of something new. Subtle changes that would later define an entirely different way of living on land. Synapsids appeared long before dinosaurs, evolving alongside early reptiles rather than after them. During much of Pangea's history, they occupied a wide range of ecological roles. Some grew quite large, rivaling reptiles in size and dominance. Others were smaller, cautious animals that avoided open ground and active competition. Over time, it was these smaller, less conspicuous forms that carried forward the traits that would eventually lead to true mammals. The environment they inhabited was not forgiving. Much of Pangea's interior was dry, exposed, and subject to long seasonal extremes. Food availability fluctuated. Water was often scarce. Predators were present, many of them larger and better armed. In this setting, survival did not favor boldness. It favored caution, flexibility, and efficiency. Early mammal ancestors were shaped by these pressures. Their bodies tended to be compact. Limbs were positioned in ways that allowed quick bursts of movement rather than sustained speed. Many likely moved with a low profile, hugging the ground or slipping through vegetation. Their small size was not a disadvantage. It reduced food requirements and made shelter easier to find. One of the most important developments within these animals was the gradual refinement of their jaws and teeth. Unlike reptiles, which often had relatively uniform teeth, synapsids began to develop differentiated dentition in sizes. Canines and grinding teeth appeared, allowing more efficient processing of food. This was not a dramatic leap, but a slow adjustment that improved dietary flexibility. With better teeth came better digestion. Early mammal ancestors could extract more energy from the same amount of food, an advantage in environments where resources were limited. This efficiency allowed them to survive on insects, small vertebrates, and plant material depending on availability. Being a generalist was safer than relying on a single food source. Another subtle shift occurred in posture and movement. While many reptiles sprawled their limbs to the sides, some synapsids began to bring their legs slightly underneath their bodies. This posture improved stability and breathing during movement. It also allowed for more controlled, agile motion. At the time, this change did not make them dominant runners, but it helped them navigate uneven terrain and escape danger more effectively. Sensory systems began to improve as well. Hearing became more refined as bones in the jaw gradually took on new roles in sound transmission. Smell likely played a crucial role, helping these animals locate food, recognize mates, and detect predators. Vision adapted to low-light conditions, suggesting that many early mammal ancestors were active during dusk, night, or early morning. This shift toward nocturnal or crepuscular activity was a key survival strategy. By avoiding the hottest parts of the day and the most active predators, early mammal ancestors reduced competition and risk. Darkness provided cover. Cooler temperatures reduced water loss. Nighttime activity matched their developing sensory strengths. Shelter was essential. Burrowing behavior became increasingly important. Digging into soil provided protection from temperature extremes and predators alike. Burrows also offered stable environments for resting and possibly for raising young. These underground spaces buffered animals from the long, harsh seasons that defined Pangea's interior. Reproduction strategies evolved quietly but significantly. While early mammal ancestors still laid eggs or gave birth to relatively undeveloped young, there was a growing emphasis on parental care. Protecting offspring increased survival rates, even if it limited how many could be produced at once. This trade-off favored quality over quantity, a hallmark of later mammalian life. Skin and body covering also began to change. While full fur not yet evolved, evidence suggests that some synapsids developed hair-like structures, possibly initially for sensory purposes rather than insulation. These structures helped animals navigate dark environments and detect movement. Over time, they would also contribute to temperature regulation. Metabolism gradually shifted. While not yet fully warm-blooded, early mammal ancestors showed signs of increased internal temperature control. This allowed more consistent activity levels, especially during cooler nights or seasons. Maintaining body temperature required energy, but the improved efficiency of digestion helped offset this cost. Despite these advantages, early mammal ancestors were not immune to environmental upheaval. Pangea experienced periods of significant stress, including volcanic activity, climate shifts, and mass extinction events. One of the most severe occurred near the end of the Permian period, wiping out a large proportion of life on Earth. This event dramatically reshaped ecosystems. Many dominant synapsid lineages disappeared. Reptiles, including early dinosaurs, expanded into newly available niches. The mammal ancestors that survived were often the smallest and most adaptable, those already living in marginal spaces and relying on flexible strategies. Survival through such events further refined mammalian traits. The ability to endure scarcity, reproduce reliably, and recover quickly became crucial. These survivors did not rebound by growing larger or more aggressive. They persisted by remaining small, cautious, and efficient. The landscapes they moved through bore the marks of stress. Vegetation thinned in some regions. Deserts expanded. Forests retreated toward coasts and river systems. In these altered environments, early mammal ancestors followed resources rather than territory. Their footprints in the dust were temporary, constantly shifting with conditions. Interactions with reptiles continued to shape their lives. Reptiles dominated open environments and daylight hours. Mammal ancestors occupied edges, understory, and nighttime niches. This division reduced direct competition, but also limited opportunities. Success depended on exploiting what others ignored. Over millions of years, these quiet strategies accumulated into profound change. Jaw structures continued to refine. Earbuds shifted fully into hearing roles. Brain regions associated with sensory processing, and behavior expanded gradually. These changes were incremental, invisible within a single lifetime, but transformative across geological time. Social behavior likely remained simple. While some parental care existed, complex group structures were probably rare. Solitary or loosely associated lifestyles suited environments where resources were scattered. Communication relied on scent, touch, and simple vocalizations rather than elaborate displays. The evolutionary path of early mammal ancestors was not straightforward. Many lineages experimented with different forms and lifestyles, only to vanish later. The line that led to modern mammals was not obviously superior at the time. It survived largely because it was flexible and resilient rather than dominant. As Pangea slowly began to change with tectonic forces preparing to fragment the land, new pressures emerged. Climates became more variable. New habitats formed along rift zones and shallow seas. These changes created opportunities for adaptation, but also new challenges. Early mammal ancestors were well positioned to respond. Their small size allowed them to move into newly formed environments quickly. Their sensory adaptations suited complex changing landscapes. Their reproductive strategies supported recovery after disruption. Still, they remained in the background. Dinosaurs would soon rise to prominence, reshaping terrestrial ecosystems and further pushing mammal ancestors into marginal roles. Yet the foundations laid during this long period on Pangea would prove essential. The footprints left by these animals were light, easily erased by wind, rain, and time. But they were consistent. Generation after generation moved through the same landscapes, adapting quietly, carrying forward traits that would eventually allow mammals to thrive in a far more fragmented and dynamic world. The Great Dryness did not arrive all at once, and it did not announce itself with a single catastrophic moment. Instead, it crept across Pangea slowly, settling into the land the way heat settles into stone. Over millions of years, vast regions of the supercontinent became progressively drier. Not because rain vanished entirely, but because it became unreliable, uneven, and separated by long stretches of absence. For life living far from the coasts, this gradual drying reshaped everything from how plants grew to how animals moved, fed, and endured. At the center of Pangea, distance itself was the enemy. Moisture carried inland from the surrounding ocean lost strength with every kilometer traveled. Clouds that formed over coastal waters released their rain long before reaching the interior. What remained was dry air, sweeping winds, and a sun that faced little resistance from cloud cover. The result was a landscape where water existed, but rarely where or when it was needed most. This dryness was not uniform. Some regions experienced prolonged arid conditions, while others oscillated between dry and semi-wet phases over long climatic cycles. But even in areas that did receive occasional rain, the timing was unpredictable. Seasons stretched, droughts lingered. Life adapted not to scarcity alone, but to uncertainty. Plants were the first to confront this challenge. In earlier, wetter phases of Pangea, forests had spread widely across lowlands and river systems. As dryness intensified, these forests retreated. Trees clustered more tightly around reliable water sources, leaving behind open ground where only the hardiest plants could survive. Leaves became tougher. Growth slowed. Reproduction shifted towards strategies that favored survival during long, unfavorable periods. Seed-producing plants gained an advantage. Seeds could remain dormant, waiting months or years for suitable conditions to germinate. Spores, while abundant, were more vulnerable to prolonged dryness. This shift subtly altered plant communities, favoring species that invested energy in fewer, more resilient offspring rather than sheer numbers. Root systems changed as well. Plants that survived the great dryness often sent roots deep into the soil, tapping moisture stored far below the surface. Others spread roots widely, capturing brief rainfall before it evaporated. These adaptations shaped the structure of entire ecosystems, influencing soil stability, erosion, and nutrient cycling. Open landscapes expanded. What we might loosely call deserts began to dominate large portions of the interior. These were not always sandy dunes. Many were rocky plains, dry grassless expanses, or scrublands dotted with sparse vegetation. The ground hardened under repeated exposure to sun and wind, making water infiltration difficult even when rain did fall. Animals living in these regions faced constant pressure. Amphibians declined sharply, unable to reproduce reliably without standing water. Those that remained clung to shrinking wet refuges along rivers and seasonal pools. Reptiles better adapted to dryness became increasingly dominant. But even they were not immune to stress. Food webs simplified under these conditions. Plant productivity declined, reducing the energy available to herbivores. Herbivore populations thinned, which in turn affected predators. Survival depended less on abundance and more on efficiency. Animals that could survive on minimal food, tolerate dehydration, or enter states of reduced activity had an advantage. Burrowing became one of the most effective survival strategies. Underground, temperature extremes softened. Moisture lingered longer. Predators were easier to avoid. Many reptiles' early mammal ancestors and insects relied heavily on burrows, emerging only during favorable conditions. The land above ground often appeared quiet, but beneath it life persisted. Movement patterns changed. Rather than roaming widely, many animals adopted localized ranges centered around reliable resources. Migration still occurred, but it was often slow and incremental, shifting with changing conditions rather than following strict seasonal routes. Rivers became lifelines, corridors of relative stability, cutting through otherwise hostile terrain. Insects responded to dryness with remarkable adaptability. Many species reduced active periods, emerging only briefly after rain. Eggs and larvae entered dormant states, waiting patiently. Thick exoskeletons reduced water loss. Feeding shifted toward detritus, fungi, or hardy plant material that persisted through drought. Dust became a defining feature of the great dryness. Winds sweeping across exposed land lifted fine particles into the air, carrying them across vast distances. Dust storms darkened skies, reduced sunlight, and coated vegetation. While harsh in the short term, this dust also transported minerals, enriching soils far from their source. The atmosphere itself changed under prolonged dryness. Reduced vegetation altered carbon cycling. Less plant growth meant less carbon dioxide absorption, contributing to warming. Warmer temperatures increased evaporation, reinforcing dryness. These feedback loops were slow but powerful, locking regions into arid states for extended periods. Water bodies shrank. Lakes became seasonal. Rivers fluctuated dramatically, swelling after rain and dwindling to trickles during drought. Aquatic ecosystems fragmented. Fish and amphibians faced repeated bottlenecks, with populations collapsing and recovering in cycles that favored rapid reproduction and resilience. Reproduction across many species became opportunistic rather than breeding on fixed schedules. Animals reproduced when conditions allowed. This strategy reduced wasted energy and increased the likelihood that offspring would survive. Parental care, where present, became even more valuable, protecting young through unstable periods. The Great Dryness also reshaped interactions between species. Competition intensified around limited resources. Predation pressure fluctuated as prey became scarce. Some predators shifted diets or hunting strategies. Others declined. These changes did not unfold quickly, but they accumulated gradually, altering which species dominated which environments. Extinction during this time was often quiet. Species did not necessarily vanish in dramatic events. Instead, populations dwindled over long periods, failing to reproduce successfully or adapt quickly enough. Fossil records from arid regions often show gaps reflecting these slow disappearances rather than sudden die-offs. Yet the Great Dryness was not purely destructive. It acted as a powerful filter, favoring traits that would prove valuable long into the future. Water conservation, efficient metabolism, flexible behavior, and resilience under stress became defining characteristics of surviving lineages. Early mammal ancestors, already adapted to marginal conditions, endured this period by remaining small, nocturnal, and resource-efficient. Their reliance on burrows, varied diets, and parental care helped them survive where larger, more specialized animals could not. Plants that survived carried forward drought-resistant traits that would later shape ecosystems on newly separated continents. Reptiles refined their dominance of dry land, setting the stage for future evolutionary expansions. Insects continued to anchor food webs even as conditions grew harsh. The Great Dryness also influenced the planet's future geography. Reduced vegetation increased erosion, transporting sediment into low-lying areas and shallow seas. Over time, these processes altered landscapes, contributing to changes in sea level and coastal environments. As Pangea slowly began to fracture, the Great Dryness did not end immediately. In some regions, it intensified. In others, new moisture sources appeared as rift zones opened and shallow seas formed. This uneven transition created new ecological gradients, testing species in different ways. Life responded as it always had through gradual adjustment rather than sudden transformation. Species ranges shifted, behaviors adapted, communities reorganized. The struggle to survive did not produce a single winner, but it refined the rules of survival itself. By the time the supercontinent's unity began to weaken, life on Pangea had already been shaped by prolonged hardship. The Great Dryness had taught ecosystems to endure, to wait, and to make use of every opportunity when it arose. For most of its existence, Pangea gave the impression of permanence. The land was vast, continuous, and seemingly stable. And for countless generations of living things, there was no reason to imagine it could ever be otherwise. Yet deep beneath the surface, forces were at work that cared nothing for appearances. The same slow movements that had once drawn continents together were beginning to reverse, and the planet itself was preparing for a long, uneven act of separation. The process did not begin with dramatic cracks splitting the land in two. There were no sudden chasms opening overnight, no immediate oceans pouring in. Instead, the change started quietly far below the ground, where heat from Earth's interior continued to rise. Over time, this heat weakened the crust beneath Pangea, especially in regions where the supercontinent was thick and heavy. The land above responded almost imperceptibly at first, lifting slightly, stretching subtly, straining under forces that would take millions of years to fully express themselves. From the surface, life would have noticed very little at the beginning. Forests still grew where they always had. Deserts still baked under the sun. Rivers still followed familiar paths. But small changes were accumulating. In some areas, the ground began to rise, creating broad uplifts rather than sharp mountains. In others, long, shallow depressions formed, barely noticeable in a single lifetime, but persistent over generations. These early rift zones were the first visible hints that the land was no longer entirely at rest. They often appeared as elongated valleys stretching hundreds or even thousands of km. The ground within them thinned as the crust was pulled apart, and magma from below moved closer to the surface. Volcanic activity increased along these zones, releasing lava, ash, and gases into the air. Volcanoes during this time did not always form tall, explosive peaks. Many eruptions were fissure eruptions, where lava poured out of long cracks in the ground, spreading across the landscape in wide sheets. These lava flows reshaped terrain gradually, burying older surfaces and creating new hard rock plains. Life responded by retreating, adapting, or recolonizing once conditions stabilized. The release of volcanic gases had global consequences. Carbon dioxide levels rose, contributing to warming. Sulfur compounds entered the atmosphere, affecting cloud formation and rainfall patterns. These changes unfolded slowly, but they added new pressures to ecosystems already shaped by dryness and long seasons. As the crust stretched further, some rift zones sank, forming low-lying basins. These basins collected water, creating lakes or shallow seas where none had existed before. For life, these new environments were both opportunity and challenge. Aquatic organisms expanded into fresh habitats. Terrestrial species adjusted movement patterns to account for new barriers and resources. These early bodies of water were often temporary. As tectonic activity continued, some basins deepened and stabilized. Others dried out or filled with sediment. The landscape became more varied, introducing complexity to regions that had once been relatively uniform. One of the most significant consequences of stretching was the gradual weakening of Pangea's interior. The supercontinent had been held together by thick, strong crust formed during earlier collisions. As heat accumulated beneath it, that strength diminished. The land began to behave less like a single rigid block and more like a material under tension capable of bending, thinning, and eventually breaking. This tension did not resolve evenly. Certain regions became focal points of stress influenced by older geological structures, differences in crustal thickness, and mantle dynamics below. These regions would later define where continents ultimately separated. At the time, however, they were simply areas of persistent geological activity. Life responded to this changing world in subtle ways. Increased volcanic activity periodically disrupted ecosystems, but it also enriched soils with minerals. Fresh lava, once weathered, provided nutrients that supported plant growth. In some regions, forests rebounded more vigorously after volcanic episodes, benefiting from renewed soil fertility. New water sources altered local climates. Areas near rift lakes or shallow seas experienced increased humidity and more moderate temperatures. These zones became refuges during dry periods, concentrating life and increasing competition. Species that could exploit these refuges gained advantages that would shape future evolutionary paths. Animal movement patterns adjusted. Where once uninterrupted land allowed gradual dispersal, emerging rift zones and water bodies introduced partial barriers. They did not completely isolate populations, but they slowed gene flow and created conditions for divergence over long spans of time. This would lead to increased regional variation for early mammal ancestors and small reptiles. These changes created new opportunities. Complex terrain favored agility, sensory awareness, and flexibility. Burrowing remained valuable, but so did the ability to navigate varied landscapes. Populations began to differentiate slightly, adapting to local conditions rather than remaining broadly uniform. Plants responded by adjusting ranges. Species adapted to wetter conditions expanded into new lowlands. Drought-tolerant plants persisted in uplands and interiors. Over time, vegetation patterns became more patchy, reflecting the growing complexity of the land. The oceans responded as well. As rift zones deepened and widened, seawater began to intrude farther inland. Shallow marine environments formed along the edges of the supercontinent and within its interior. These new seas altered circulation patterns, introducing moisture into regions that had long been dry. Ocean currents began to change. Even small openings in the land allowed water to move differently, redistributing heat and nutrients. These shifts influenced climate on a regional scale, softening extremes in some areas while introducing new variability in others. Importantly, the breaking of Pangea was not a single event, but a sequence of related processes unfolding over tens of millions of years. Some regions began to separate, while others remained firmly connected. The supercontinent entered a transitional state, neither fully unified nor fully divided. For life, this transitional phase was challenging. Long-standing environmental stability gave way to increased variability. Weather patterns shifted. Resources redistributed. Habitats fragmented gradually. Species that had thrived under consistent conditions now face new pressures. Extinction rates increased in some groups, not because of sudden catastrophe, but because slow change favored different traits. Species unable to adjust ranges or behaviors declined. Others adapted and spread into newly available niches. This period also set the stage for future isolation. As rifts widened and seas deepened, populations that had once been continuous became separated. Over time, these separations would allow evolution to proceed along different paths on different land masses. Yet during the early stages, the land still felt largely connected. Travel across Pangea remained possible. Rivers still flowed across broad regions. Life retained a sense of continuity, even as the foundations of that continuity weakened. The stretching and tearing of the Earth introduced a new tempo to the planet's story. Change became more frequent, though still slow by human standards. The long, steady breathing of Pangea gave way to uneven movements, pauses, and surges. Volcanism remained a constant companion during this time. In some regions, massive volcanic provinces formed, covering enormous areas with lava over extended periods. These events released vast amounts of gas, influencing global climate and contributing to environmental stress. Life endured these challenges by drawing on traits refined during earlier hardships. Water conservation, flexible behavior, efficient metabolism, and resilience under stress continue to matter. Those that possessed these traits were more likely to survive the transition. As the land stretched further, fractures widened. The outlines of future continents began to emerge, though they would not resemble modern shapes for a very long time. The idea of edges, once absent, slowly returned to the planet. For organisms living through this era, the world did not suddenly become unfamiliar. It changed piece by piece. A new valley here, a lake there, a shift in rainfall patterns, a new migration obstacle. Each generation adapted to slightly altered conditions, carrying forward what worked and leaving behind what did not. This slow unmaking of Pangea marked the beginning of a new phase in Earth's history. It did not erase the past. It built upon it, reshaping landscapes and life in ways that reflected both continuity and change. As the supercontinent continued to strain and separate, the planet prepared to enter a more complex, more varied world. The long unity that had defined life for so many millions of years was giving way to diversity, fragmentation, and opportunity. And as this process continued, the living world, shaped by patience and endurance, was already beginning to respond to a future it could not yet fully see. Life on Pangea did not vanish when the supercontinent began to break apart. It did not reset, restart, or reinvent itself from nothing. Instead, it carried forward habits, structures, and solutions that had been refined over hundreds of millions of years. The living world we recognize today is not separate from that ancient unified Earth. It is built directly on it, shaped by the pressures, experiments, and compromises that life learned while the land was still one. Many of the most basic patterns that define modern ecosystems were first established during the time of Pangea. The way plants manage water, the way animals move across land, the way food webs organize themselves under constraint, and even the way climates influence biology all trace back to that long era of unity. Pangea acted as a testing ground, forcing life to solve problems at continental scale before fragmentation made environments smaller and more varied. One of the most enduring legacies of Pangea is how life learned to deal with dryness. Large portions of the supercontinent were far from the sea, exposed to long periods of low rainfall and intense seasonal variation. Plants that survived there developed strategies that remain widespread today. Deep root systems, waxy leaf coatings, tough tissues, and slow conservative growth patterns are all solutions forged under Pangea's conditions. These traits did not disappear when continents separated. They spread, diversified, and adapted to new regions, shaping modern deserts, grasslands, and dry forests. Seed-based reproduction, in particular, became a dominant strategy during and after Pangea. Seeds allowed plants to pause their life cycle, waiting for favorable conditions. This ability proved invaluable as climates became more variable during continental breakup. Today, nearly all terrestrial ecosystems depend on seed plants that trace their success back to adaptations refined on the supercontinent. Animals, too, carry Pangea's imprint. Reptiles that mastered life on dry land established the blueprint for terrestrial dominance. Waterproof skin, shelled eggs, efficient kidneys, and flexible metabolism all emerged as responses to Pangea's harsh interior. These features allowed reptiles to spread widely and later diversify into dinosaurs, birds, and modern reptilian lineages. Even mammals, which would remain in the background for much of the dinosaur era, owe their success to lessons learned during Pangea. Early mammal ancestors evolved under constant pressure to conserve energy, avoid competition, and survive scarcity. Traits such as differentiated teeth, improved hearing, nocturnal habits, and parental care were not luxuries. They were necessities shaped by long struggle. When environments later became more fragmented and unpredictable, these traits gave mammals an advantage. The structure of modern food webs also reflects Pangea's influence. On a unified landmass, ecosystems favored generalists over extreme specialists. Species that could exploit a range of resources were more likely to survive long-term environmental stability punctuated by gradual change. This pattern persists today. Many successful modern animals and plants remain adaptable, capable of shifting diets, behaviors, or habitats when conditions change. Insects provide one of the clearest examples of continuity. Their dominance during Pangea established them as the backbone of terrestrial ecosystems. Decomposition, soil formation, pollination, and nutrient cycling all depended heavily on insects long before flowering plants appeared. When flowers eventually evolved, insects were already primed to exploit them, leading to the explosive diversification that defines modern terrestrial life. That partnership was not created from scratch. It grew from relationships and behaviors shaped on Pangea. The oceans, too, carry Pangea's legacy. Marine species that evolved in the vast connected waters of Panther Lassa developed broad tolerances and wide distributions. When continents separated and new ocean basins formed, these organisms diversified into regional forms. Coral reefs, fish communities, and marine food webs all reflect an origin in large connected systems, followed by fragmentation. Climate patterns inherited from Pangea also influenced Earth's future. The supercontinent demonstrated how land arrangement affects global circulation. When Pangea broke apart, newly formed oceans and coastlines transformed climate dynamics, introducing more frequent weather changes and regional variability. Life that had survived long, stable conditions now faced a world of shifting environments, seasonal unpredictability, and isolated habitats. This transition rewarded flexibility. Species that could migrate, adapt behaviorally, or evolve quickly thrived. Others declined. The mass extinctions that occurred during and after Pangea's breakup were not random. They filtered life according to traits that had been shaped long before during the supercontinent's reign. The distribution of fossils across modern continents provides direct evidence of Pangea's lasting influence. Similar plant and animal fossils appear on land masses now separated by oceans. Not because those organisms crossed vast seas, but because they evolved when no such seas existed. This shared history explains why ecosystems on different continents still show deep similarities despite millions of years of separation. Mountain ranges formed during Pangea's assembly continue to shape modern geography. Though eroded and transformed, these ancient structures influence rainfall patterns, river systems, and biodiversity today. The Appalachian Mountains in North America, for example, share origins with ranges in Europe and Africa, remnants of a time when those lands were joined. Soils developed under Pangea's forests and drylands also left a legacy. The long accumulation of organic matter, the influence of ancient vegetation, and the role of insects and microbes established soil profiles that later ecosystems inherited. Even after continents drifted apart, these foundational layers influence what could grow where. The concept of ecological succession, how environments recover and reorganize after disturbance, was refined on Pangea. Wildfires, droughts, volcanic eruptions, and sea level changes repeatedly reshaped landscapes. Life learned not just to survive disturbance, but to use it. Many modern ecosystems still depend on cycles of disruption and recovery, first experienced during the supercontinent's long history. Behavioral patterns, too, reflect ancient origins. Migration along environmental gradients, seasonal breeding time to resource availability, borrowing, nocturnal activity, and social flexibility all gained importance under Pangea's conditions. These behaviors persist because they work across many environments, not just specific ones. Even the pace of evolution itself was shaped by Pangea. Long periods of stability encouraged gradual change, rather than rapid bursts of innovation. When fragmentation introduced isolation and new pressures, evolution accelerated, building on a deep foundation of established traits. This combination of slow preparation and later diversification explains much of Earth's biological richness today. Modern biodiversity hotspots often align with regions that experienced complex histories during and after Pangea's breakup. Areas where climates shifted, seas advanced and retreated, and mountains rose and eroded became centers of adaptation and diversification. Life there reflects both ancient resilience and later experimentation. Human existence, though recent, is not separate from this story. Our own physiology, dependence on certain plant groups, and vulnerability to climate patterns are indirect results of Pangea's influence. The distribution of crops, the behavior of pests, the structure of forests and grasslands all trace back to evolutionary pathways shaped on a unified Earth. Understanding Pangea's role helps explain why life responds to environmental change the way it does today. The tendency for species to migrate rather than adapt instantly. The importance of refugees, the uneven impact of climate stress, and the resilience of generalist organisms all reflect ancient strategies. Pangea's life shaped the world not by creating a finished product, but by establishing rules. Rules about how to survive dryness, how to manage long seasons, how to endure scarcity, how to persist through slow change. Those rules continue to govern life. Even as the stage on which it plays has become more fragmented and dynamic as continents drifted apart, life did not forget its time on a single landmass. It carried that memory forward in genes, behaviors, and ecosystems. Every forest, desert, reef, and grassland today contains echoes of that ancient world, shaped by lessons learned when Earth still had no edges. As the land that had once been whole continued to separate, the change did not feel abrupt to the living world. There was no single moment when Earth crossed a clear line between unity and division. Instead, the continents drifted apart at a pace so slow that no organism could witness the full transition within a lifetime. The world did not shatter. It loosened, stretched, and gradually redefined itself, carrying with it a long memory of what it had been before. The drifting of continents reshaped Earth's surface in ways that went far beyond geography. As rift zones widened into seas and shallow oceans deepened into permanent basins, the planet gained edges it had not known for hundreds of millions of years. Coastlines multiplied. Currents changed direction. Winds encountered new obstacles. Climate once dominated by vast interior land masses, and slow rhythms became more complex and less predictable. For life, this new complexity was both disruptive and rich with possibility. Environments that had once been connected were now separated by water. Populations that had mixed freely across Pangea became isolated, sometimes by narrow seaways at first, then by widening oceans. Over time, isolation allowed differences to accumulate. Species began to diverge, adapting to local conditions rather than continental ones. This process did not erase the influence of the past. The organisms that found themselves on newly forming continents carried with them traits shaped during the Age of Unity. Their bodies, behaviors, and ecological roles were not newly invented. They were inherited. The memory of Pangea lived on not as awareness, but as biology. As continents drifted, climate zones shifted as well. Areas that had once been deep interior became coastal. Regions that had relied on distant moisture sources now sat beside new seas. Rainfall patterns changed accordingly. Some deserts softened. Some forests expanded. Others vanished. These changes unfolded unevenly, creating mosaics of opportunity and stress. The oceans that formed between separating land masses altered global circulation. Instead of one dominant ocean, multiple basins began to develop, each with its own currents, temperature gradients, and nutrient flows. Heat distribution across the planet became more efficient in some ways, more variable in others. Seasonal patterns grew sharper. Storm systems became more localized and more frequent in certain regions. Marine life responded quickly. New coastlines created extensive shallow water habitats, fueling bursts of productivity. Coral reefs expanded in newly favorable regions. Fish diversified as populations became separated by emerging barriers. What had once been broad, uniform marine communities fragmented into regional ecosystems, each following its own evolutionary path. On land, fragmentation reshaped competition. Species that had once coexisted across vast areas now found themselves limited to smaller ranges. Resources that had been abundant somewhere on the supercontinent might now be absent entirely from a given land mass. This forced adaptation or decline. Migration became more important and more constrained. On Pangea, gradual movement across land allowed species to track favorable conditions over generations. With continents separating, migration routes narrowed or disappeared. Some species adapted to new climates. Others followed coastlines or mountain ranges. Those unable to move or adapt vanished quietly. The rise of more complex ecosystems followed. With increased isolation came specialization. Plants adapted to specific soils, climates, and pollinators. Animals evolved tighter relationships with particular food sources or habitats. This specialization increased biodiversity, but it also increased vulnerability. Local disruptions now carried greater risk. Despite this growing complexity, echoes of the ancient unified world persisted. Many plant lineages retained drought tolerance, a reminder of life far from ancient seas. Animals continued to use burrowing, nocturnal activity, and flexible diets as strategies forged during long hardship. Insects remained ubiquitous, anchoring food webs as they had before. The structure of ecosystems still reflected Pangea's influence. Even as forests became more diverse, their vertical layering echoed ancient patterns. Predator-prey relationships retained dynamics shaped by earlier scarcity. Fire, drought, and disturbance remained familiar forces, now interacting with new geography rather than replacing old lessons. Mountains continued to rise and erode as continents moved. Some ranges formed where land masses collided after drifting apart. Others wore down, leaving behind plateaus and plains. These features influenced rainfall, river systems, and biodiversity, further diversifying habitats. Yet many mountain routes traced back to structures formed during Pangea's assembly. The fossil record preserves this continuity. Similar lineages appear on widely separated continents, diverging only after drift created distance. This shared ancestry explains why ecosystems across the globe still feel related despite their differences. Life diversified outward from a common foundation rather than starting anew. Over time, dinosaurs rose to dominance, filling niches that had once belonged to earlier reptiles. Mammal ancestors remained mostly small and hidden, but the traits refined during Pangea allowed them to endure. When dinosaurs later disappeared, mammals were prepared to expand, drawing on strategies developed long before continents had edges. The quiet echo of Pangea can be felt in how life responds to change today. Species still migrate when climates shift. Ecosystems still reorganize gradually rather than instantly. Generalists often survive upheaval better than specialists. These patterns are not accidents. They're inherited responses shaped during a time when change was slow, vast, and unavoidable. Even Earth's current configuration reflects this legacy. The distribution of continents influences modern climate just as Pangea once did. The arrangement of land and sea continues to govern atmospheric circulation, ocean currents, and seasonal rhythms. The planet still remembers how geography shapes life. Human history occupies only the thinnest layer atop this story. Agriculture depends on plants whose ancestors adapted to ancient dryness. Our bodies reflect mammalian traits forged under reptile dominance. Our vulnerability to climate change echoes challenges life has faced many times before, though now at a pace far faster than natural systems evolved to handle. Understanding the drifting of continents is not only about reconstructing the past. It helps explain why life behaves the way it does in the present. The quiet echo of an ancient Earth guides responses to stress, recovery, and opportunity. It reminds us that stability and change are not opposites, but partners in a long process. As continents continue to move today at rates measured in time per year, the planet remains dynamic. New mountains will rise. New seas will form. Old ones will close. Life will respond as it always has, drawing on deep memory while adapting to new circumstances. The world no longer has a single landmass, but it carries within it the imprint of that time. every forest shaped by seasonal drought, every animal adapted for endurance, every ecosystem built on layered resilience reflects lessons learned when Earth was whole. The drifting continents did not erase Pangea. They transformed it. And in doing so, they carried forward a quiet echo that continues to shape the living world. A reminder that even as the surface of the planet changes, the deeper patterns of life persist, linking the present to an ancient Earth that still speaks through the land beneath our feet.